given a complex number z1 and then the modulus of the products and the argument of the products of z1 and z2. So first thing I'm going to do is, well, actually asks us to write z1 in polar form. And let's use sort of the general definition. Here's my complex number. It's got x, it's got y, it's z equals x plus iy. Then the magnitude I use Pythagoras for, x squared plus y squared. We ignore the imaginary part because this is the imaginary axis. I basically find the distance from the origin to the complex number and I square root there. So let's do that. The modulus of z1 is going to be 2 squared plus 3 squared square rooted 4 plus 9 root 13. Now for the arguments. Well, I can say that tan, I'll call it theta, tan of theta is equal to y over x. And this still applies whether it's down here or over here. In fact, it's in the first quadrant here, but just to say you can still use it. You just have to put in a negative for y or x, depending on what you have. So tan theta is y over x, and that means theta is going to be inverse tan, in this case, 3 over 2. And that ends up being 0.98279. I'll just do it on my calculator as well. Inverse tan 3 over 2. Okay, I've got it stored now. Right, so then finally, z1 becomes root 13 multiplied by cos 0.9828 plus I sine 0.9828. So the cos part is actually my real component, because if I take this and I just find the component in the horizontal direction, that's what you'd get with cos, and then the vertical component with sine. So now for the next part, find z2. And there's a couple of ideas that we can use. So the modulus of z2 is simply going to be the modulus of z1, z2 over the modulus of z1. And we know both of these, 39 root 2 over root 13. This is actually, let's just put it in our calculator. You could write 39 as 3 times 13 and do it non-calc, but kind of wanted to keep that. All right, 39 root 2 divided by root 13 becomes 3 root 26. And then for the arguments, when you multiply complex numbers together, you actually add the arguments together. And you can show that using addition formulae. I'm not going to do that here, but it's just a fact to be aware of. What that means is if I want the argument of z2, I'm going to subtract. It's going to be the argument of z1, z2 minus the argument of z1. So pi over 4 minus 0.98279 and so on. But I think I want the exact one, especially because of what is going to come in a minute. So then I can do pi over 4 minus answer, which gives me minus 0.1973. So that means that z2 is going to equal 3 root 26 times cos of this plus I sine minus 0.1973. But we want it back in Cartesian form, a plus ib. So I'm actually going to just store it to my memory for a second, and then I'm going to do 3 root 26 times cos. I could do answer or I could use a memory now. We get 15. Now, if you don't keep it exact, actually it will be 15 point something. And they've asked us for whole numbers, so you probably figure out that it is going to be 15, but we've just shown it absolute certainty now. It's going to be 15. And then I want I sine, also just sine, so 3 root 26. We don't need to go into any more detail on this. You know, the fact that we get it is absolutely fine. So sine, and that gives me minus 3. So 15 minus 3i, that is our Z2.